Hello, Mr. Betts here. I want to take a look at a few examples of Maclaurin polynomials, and we're going to get these by taking functions and manipulating them in certain ways. So this one, if we recognize that this function can be written as 1 plus x times 1 over 1 minus x, we know the Maclaurin polynomial for 1 over 1 minus x, which is, I'll write this underneath here. So geometric series, we have 1 plus x squared plus x cubed, and I'm gonna go to the fourth degree just in case I need it here, because we are writing a fourth degree Maclaurin polynomial for the whole thing. So this is going to be then equal to 1 plus x times that. So to get the Maclaurin polynomial that we're looking for here, we're going to distribute that 1 plus x. So we have 1 times 1 is 1. Then for the x to the first term, we're going to have 1 times x and x times 1. So that's going to give us a plus 2x for both of those added together. For our second degree term, we're going to have 1 times x squared, and we're going to have x times x. So we're going to have 1x squared plus x squared, so that'll be plus 2x squared. Then for our next one, our x to the third degree term, we're going to have 1 times x cubed, and we'll have x times x squared. I think maybe at this point you might be seeing a pattern. So we're going to have x cubed plus x cubed, which is 2x cubed. The same thing's going to happen with the x to the fourth. So we're going to have 1 times x to the fourth, and x cubed times x gives us plus 2x to the fourth. And we can stop because we're looking for the fourth degree Maclaurin polynomial. I'm going to identify it. Usually if we're doing a degree, we'll use a subscript to show it's a fourth degree. So we get 1 plus 2x squared plus 2x cubed plus 2x to the fourth, and so on. In the next example, we want a third degree Maclaurin polynomial for the function e to the x times cosine of x. No tricks here, just going to have to do kind of the same thing we did in the last one. We just have to know that the Maclaurin polynomial for e to the x is 1 plus x squared over 2 factorial, which I'm going to write as just x squared over 2 plus x cubed over 3 factorial. And I'm not going to go any further because I know with a third degree, I'm not going to get a third degree term by multiplying by an x to the fourth term. So I can stop there. And then for cosine of x, remember the Maclaurin polynomial for cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. I don't even need that x to the fourth term. In fact, I'm going to avoid confusion, just get rid of that. And now we want to distribute. So for the x to the 0 term, we're going to have 1 times 1, which is 1. For the x to the first term, we're going to have, well, we don't get anything here, 1 times nothing there because we don't have an x to the first term, but we are going to have x times 1 here, so that's going to be plus x. For the x squared term, we're going to do 1 times x squared over 2, and then we're going to have 1 times x squared over 2, so that's x squared over 2 plus x squared over 2, which is x squared. Then we're going to have, for the third degree term, it may be tempting at this point to say, oh, maybe this is going to be 1 over 1 minus x, so plus x cubed. Be careful. Don't make assumptions like that because it may or may not work. So third power, we're going to do 1 times the third power. Don't have any. We could do x times x squared over 2, and we can do x cubed times 1. So there's a few different ways we can get a third degree term. So we're going to have x squared over 2 times x is x cubed over 2, and then plus x cubed over 6. So that's going to be 5x cubed over 6. And that's it. That's all we have to do because that's our third degree. So the third degree Maclaurin polynomial for e to the x times cosine of x is going to be that. So on this one, we have g of x is 2x times cosine of x squared. First thing I'm going to do is I'm going to write a Maclaurin polynomial for cosine of x squared. I'm going to do a substitution there. So cosine of x squared is going to be, actually, let me start with this. Cosine of x. I'm going to start simple. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. That should be a minus. And so on. We're looking for 4 non-zero terms. I think 4 terms in this should be sufficient, but we'll see. We can add more if we need to later. So now using substitution, cosine of x squared is going to be 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial, and so on. So now the last thing I'm going to do is I'm going to multiply that by 2x. So 2x times cosine of x squared. Really, I'm just distributing the 2x to each term. So it's going to be 2x, then it's going to be 2x to the 5th over 2 factorial plus 2x to the 9th over 4 factorial minus 2x to the 13th over 6 factorial, and so on. But we have our 4 non-zero terms, so that is our answer. I do want to point out that I have something here that's kind of bad. I used ellipses here and here to show those are continuing and going forever, and so these equal signs are okay. However, if I don't go on forever here, then this is not actually equal. So I'm going to modify this and put approximately equal to, or I could get away with an equal sign by just saying that the Maclaurin polynomial for g of x is equal to that. So this is a Maclaurin approximation now instead of equal to the function itself. Now, I want to do this another way. The other way I'm going to do this, I recognize here, and this is something that I wouldn't necessarily expect you to recognize, but 2x times the cosine of x squared is the derivative of the sine of x squared. So thinking about using the chain rule, the derivative of sine is cosine. We keep the x squared inside. And then with the chain rule, we multiply by the derivative of x squared, which is 2x. So this is going to be 2x times cosine of x squared. So the way I'm going to construct it this time, I'm going to start with the Maclaurin polynomial for sine of x squared. And to do that, I'm going to start with the Maclaurin polynomial for sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Then I'm going to replace x's with x squareds. So we do our substitution. So we got x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on. And then, since we're looking for the derivative of sine of x squared, we can take the derivative of the Maclaurin polynomial for sine of x squared. So we take the derivative on both sides. On the left side, we get that. On the right side, we take the derivative term by term. So 2x minus 6 times x to the 5th over 3 factorial plus 10 x to the 9th over 5 factorial minus 14 x to the 13th over 7 factorial, and so on. And I do want to point out that this is a different answer than we had. I'll come back to that. Just remembering what I said on the last one, let's get rid of this and the equal sign, and let's say that the Maclaurin polynomial for g of x is equal to this. And that's an okay answer. However, if we look at our answer here, it's not quite what we had. The 2x matches. The rest of them, not quite. So let's look at how we can make it match and confirm that it is actually the same. So notice that each of the coefficients here, the 6, the 10, the 14, can be written as 2 times something. And that something is the first number in the polynomial. So the factorial. So the 3 there cancels with the 3 there and gives us 2 factorial. The 5 cancels with the 5 and gives us 4 factorial. The 7 cancels with the 7 and gives us 6 factorial. So doing a little bit of just arithmetic manipulation, we get the exact same thing that we got here.